All right, good morning, everybody. So I have loaded homework 1 on MU Online, and the notes are there. Today we're going to work through a set of calculations related to the Parshall Flume, and we talked about the advantages of the Parshall Flume during our first class on Monday. And we're also going to talk about the basics of culverts, and hopefully we'll have enough time for me to do a brief demonstration of HY8 to set us up for some more complicated examples in class on Friday. Any announcements, questions before we move on?
So on the HY8 on the homework, so do you want us to take a screenshot of it and then add it to a PDF file?
Yeah.
Okay.
Okay, so remember that in a Parshall flume, the advantage of using this rather than a weir is that it requires less maintenance because sediment isn't going to be accumulating upstream of the flow measurement point. The water is actually accelerating through the flume, and so that helps to keep any suspended particles moving along and not accumulating. And the depth is measured at 2 points. The depth is measured in the converging section, which is where we get H sub A, and then the depth is measured in the throat section. Does anybody remember, even though the equations are all based on H sub A depth, if all of those calibrated equations are based on the depth in the converging section, why do we even bother measuring the depth of flow in the throat? If it doesn't go into the equation for flow rate, why are we measuring that downstream depth? Notice in the side view of the flume a downstream section that's pretty steep. What that does is it accelerates the flow and it causes a hydraulic jump. Some of you have had hydraulics already, some of you are taking it this semester, but a hydraulic jump is kind of a specialized condition where you have supercritical flow transitioning into subcritical flow. And if the channel downstream isn't conveying the flow away from the flume fast enough, it can interfere with the hydraulic jump. And so the reason why we're measuring H sub B is to find out if the hydraulic jump is submerged. And so the slide that I showed you previously was submergence criteria. And so you're looking at the downstream depth and the upstream depth to find out, is the downstream depth high enough that the hydraulic jump is drowned, or is the hydraulic jump flowing freely? And the reason why we have to check that ratio is, it's true, we do have these equations that says the flow rate based on the H sub A, but if the hydraulic jump is submerged, then we have to apply a correction. So that's why we're measuring the downstream depth, H sub B, is to know, do we need to apply the correction, yes or no? And if yes, how big of a correction is applied? Does that make sense to everybody? Okay, so the best way to learn how to follow this process is to work an example. And that's what we're going to do in just a moment. I showed you this diagram already in class on Monday, and it's the ratio of the downstream depth to the upstream depth. And so assuming that you do have the hydraulic jump being submerged, then you have to look up some correction based on the upper depth and the percent submergence. And so you find a correction, and then depending on what the throat width is, you may also have to apply a correction factor. And the reason for that is that this figure, for instance, is specifically calibrated for a certain size flume. That one is for a flume that has a throat width of 0.3 meters. But you'll notice there's a lot of different flume sizes. Not every flume is 30 centimeters in throat width. And so if we have a correction table or a correction figure that's specifically for the flume that we're using, that's great. But if not, we can use the correction figure from a 30 centimeter flume for other sizes by multiplying the correction amount by a correction factor. So it's kind of like, you know, if you had a 1 meter width flume, let's say, just because we've got the correction factor, a 1.22 meter width flume, you could look up the correction amount from this figure, and then if you multiplied it by 3.1, then it could be used. Even though this figure is for just 30 centimeters, you could use this figure for other flume sizes. So there's both a correction amount and a correction factor. So multiple steps, and we're going to try out all those steps here in this example. So we're still using our same figure. This figure is the 0.3 meter correction, but the given throat width that we have for our flume is 0.61. So if we go back over here, that means that if the hydraulic jump is submerged, we're going to have to utilize a correction factor of 1.8. So I'm going to write that on the board so we don't lose track of it. Correction factor is 1.8. So that's just kind of filed away in the back of our minds if it comes up. So what we have to do in this example is, first of all, do the criteria to find out how is the ratio of HB versus HA. And for a 0.61 meter flume, here's the criteria. We're in this range of 0.7. So the limit, H sub B to H sub A, is 0.7. So if it's more than that, if more than the hydraulic jump is submerged, and Q needs to be corrected. All right. So first things first is, in our specific example, let's take a look at what is the submergence, the percent submergence. What we have is the depth in the converging section is 0.45 meters, and that's the H sub A. The depth in the converging section is 0.45 meters. The depth in the throat is our H sub B, and that's 0.39 meters. So if we do 0.39 divided by 0.45, what do we get for our percent submergence? Did you bring a calculator today?
2.87.
What is it?
Our convergence is 0.87.
HB to HA is 0.87. All right. So it's 87% submerged. What's the limit that we can handle without having to correct?
0.7.
That's right. So 70% is the limit. So what that means is that the water that's flowing through this flume is impeded by the downstream depth. And so this equation that we have for what the flow rate should be as a function of the upstream depth, so here's the equation that we're going to use. It's a beauty. Let's write this on the board. Q is 0.372 times the throat width multiplied by 3.281 times the upstream depth to the power of, I've got to move this over. To the power of 1.570 times W to the power of 0.0626. Okay, so this equation would tell you the flow rate if it wasn't submerged, but it is submerged. So the flow rate's going to be less than what that predicts. So we still need to calculate what would be the free flow rate, but then we're going to subtract some of the flow to find out the actual flow rate. Okay, so what you need to do, we're going to pause for a moment. I'm going to stop talking so that you can calculate what is the free flow flow rate that would occur, and then we're going to apply the correction multiplied by the correction factor. You've got an exponent with an exponent. Okay, if you're not getting the right answer, it's probably order of operations. So if we look at this equation that we're having to substitute into, you do the exponent first, and then you multiply. And so then once you find this exponent, you have to do the multiplication before you apply the exponent. So let me show you. I did it step by step. I didn't try and combine it all at once in a calculator because it's too easy to make mistakes that way. So here it's on the screen, the order that things are being done. So anything that's in parentheses, I'm multiplying together before I apply the exponent. And you'll know that I did this exponent, this 0.026, before I multiplied the 1.57. So our free flow capacity should be 0.4151 cubic meters per second. That's what the flow rate through the flume would be if we had measured a depth in the converging section of 0.45 meters and if the downstream depth was really low. Like if we had a steep channel that's coming out of the flume or a really wide channel, like if things weren't backed up once the water gets through the flume, then the flume would be carrying 0.4151 cubic meters per second. But since the downstream channel isn't conveying flow very efficiently, and we know that because of the depth that we measured in the throat, because the hydraulic jump is submerged, we have to apply a correction factor. So that's our next step. So before we start talking about the correction factor, does anybody have a question or want to discuss this free flow capacity? Okay, so we know the free flow. Now for the correction, what we're going to do is first of all, remember that our correction factor is 1.8, because what we're doing is we're using the figure from the 0.3 meter flume, and we're going to be applying the correction amount that we get from that figure, but we don't have a 0.3 meter width flume. We have a 0.61 meter width flume, and so we're going to have to use this correction factor. That's all right, we can do that. So our submergence, our percent submergence was 0.87. So we are going to use the 87% curve along with our upper head that was measured of 0.45 meters. Now what makes this a little bit tricky is it's a log-log scale. And so we don't necessarily just have like the midpoint between two measurements. We have to think, how is this log scale where you've got between 0.1 and 0.3, for instance, the 0.2 isn't halfway. It's a little bit higher than halfway. And between 0.3 and 0.6, the 0.5 would be way up here. So in our case, we have the upstream depth that was measured at 0.45. So I've done my best to kind of estimate where that would be with this light blue line. And we carry it sideways, and we're looking for the intersection with where the 87% curve would be. So 70 is here, 72, 4, here's the 80% curve, 82, 84, 86, and so between the 86 and the 88 is 87. And so the intersection with 87 and the depth, the upper head depth measurement, and then down to the horizontal axis. Now, the correction amount that I took from that figure was 0.044 cubic meters per second. So 1.8 times that is going to be how much we have to subtract from the free flow capacity that we had determined in order to find the actual flow rate. So you take the free flow and you subtract 1.8 times what you look up off of the correction figure. And that's where this comes from. So the delta Q, the correction amount, is 0.044 cubic meters per second multiplied by 1.8. And so we're going to reduce our free flow capacity by 0.0792, which means that the actual capacity of the flume under these conditions is 0.3359 cubic meters per second. Jeffrey.
Now, I might be looking at that graph wrong, but it looks like where the blue lines meet and where you go down, it looks like it's in the 89 range. I may be wrong.
Yes, you're wrong. And it's kind of an optical illusion because the numbers are shifted to the right. So let me point out. Here's the 90% curve. Do we agree that this is the 90% curve?
Yeah.
All right. So look at where that is. So that's 90, and here's 88.
Oh.
So it's between the 88 and the 86.
Okay.
Yeah. People have made that same observation before, but it's because the numbers are below it.
Okay.
Yeah. Okay. So you have a homework problem where I'm asking you to do some things having to do with the Parshall flume. So the process is you figure out what's the size of the flume, and depending on the size of the flume, you find the equation that applies. So here's the equations for different size flumes, and then you would plug in the upstream depth versus the downstream depth to find out if the hydraulic jump is submerged and whether you're going to have to apply a correction. And if you do, the only correction factor that we have in the textbook is for the 0.3 meter width. There are flume manufacturers that probably have correction factors like this for a whole range of sizes, and having that would mean that you didn't have to use a correction factor, that you just reduce the free flow capacity by the correction amount. So if you had the right figure, then the delta Q would be correction times 1. You know, the correction factor would be 1 if you were using a figure that was specific to that width. Any questions before we move on from this example on the Parshall flume? Mm-hmm.
So, if I understand this correctly, the initial calculation is to find the ideal flow rate?
Yeah, we could call that ideal or the free flow rate. Yeah.
Okay.
And sometimes it will be that. You know, if the downstream depth is low enough, if the downstream depth is below the limit, then finished. But if the downstream depth is above the submergence criteria, then you have to go through that multi-step correction process. These are really easy to make mistakes in a quiz or an exam because of it being an exponent of an exponent with some order of operation trickiness. And so I hope that the homework will be a good chance for you to practice like what order the calculations get done. And I mean, I've said it before, but I'll say it again. I think it's good to do problems like this in steps, you know, like collapse numbers together in stages rather than just putting into your calculator and hoping that it all went in right. Because this is easier to double check in kind of like if you're auditing in an exam, you're double checking your work because you've got a little extra time. It's easy to see if you did it right the first time if you know that, well, I can see that 3.281 times 0.45 is 1.47. Yeah, that's reasonable. And then you can see what was the effect of this amount to its exponent and so on. So I encourage you to, you know, paper is cheap and so is ink. So take the time to expand it out on the page and don't try and do too much at the same time in the calculator. Okay, so that was flumes. Now we're going to talk about culverts, which is another hydraulic structure. Culverts aren't for flow measurement like flumes are, but culverts are for passing flow underneath roadways. It's the inexpensive way to get water underneath a road where the flow rate doesn't really justify building a bridge. You know, I've got a culvert at the bottom of my driveway because there's just a little bit of flow there. You know, building a bridge over the tiny ditch at the bottom of my driveway would be silly. And so this is a really economical way of passing water under roads. And the reason why we're talking about it is it's probably the thing that, like just on a sheer numbers basis, hydrologists are asked to do more than anything else is size culverts. And even though I made the distinction in our class on Monday that, you know, hydrologists do one thing and hydraulic engineers do another, sometimes hydrologists are asked to go a little bit into the hydraulics area and size culverts. You know, they would do the watershed estimation and identify the queue, but then they'd also dip their toe in the hydraulics area and size the culvert as well. And so that's why, even though this is a hydrology class, we're going to do a little bit of hydraulic design, including the culvert software that we're going to demonstrate today. So how much water gets through that pipe? Like I mentioned, my driveway, it's a 24-inch pipe. Why did I choose a 24-inch pipe? Well, it's because it wasn't that much more expensive than the 18-inch pipe. The 18-inch pipe probably would have been big enough, but having a larger pipe makes it easier to clean, so there's some maintenance advantages, and the cost difference was negligible. But it's not always where it's just going to be a little bit more. Sometimes it's going to be significantly more, and so how big of a pipe you need, or you can see here's a multi-barrel culvert, whether you need one versus two, depends on a lot of different factors, like the entrance condition. You'll notice that this has some wing walls on the side of the barrel, and those wing walls affect the flow capacity of the pipe itself. If it was just a pipe sticking out, it wouldn't be able to carry as much as if we have these wing walls kind of guiding the flow into the pipe. And we're able to account for that sort of flow settling effect as the water approaches the culvert. We need to account for how long the pipe is because there are friction loss effects. We need to have a characterization of the culvert slope because, of course, how steep the pipe is affects its capacity, as does the material properties. And backwater is talking about is the culvert, when the water is going through the culvert, is it causing pooling upstream of that entrance? You know, is the water rising as it's trying to force its way into the pipe? And even downstream can have an effect on the flow conditions as well. So this is a photo that I took in Leadville, Colorado of a multi-barrel culvert, and I really like that culvert a lot. I think it's pretty cool. It leads into the town of Leadville, and the thing that's unusual about it is that in the whole state of West Virginia, a multi-barrel culvert like this would be very uncommon. Because we have such a vegetated state with lots of trees, and they just tend to accumulate too much trash upstream. And so, as the water is we're upstream looking towards the downstream end here. So the water's flowing towards the culvert. So in West Virginia, it would be uncommon to have a multi-barrel culvert like this because logs would get stuck across the width like that. But in Colorado, I mean, in this particular watershed, there isn't as much vegetation, and so they don't have the same debris accumulation problem as we might. This is the downstream view. So these are the pipes that are extending, and the water kind of plunges back into the river after it comes out of the culvert. Culverts can sometimes look a lot like bridges. This is a concrete box culvert that probably has quite a bit of structural strength, where you're not going to need as much cover over the top of a culvert like this as you would for a pipe. And even this pipe, it's kind of shocking how little cover they have over the top of that pipe. The strength of a culvert partly comes from as it begins to flex and it's compressing the soil on the edges. As it begins to deform, it gains strength as it has that elliptical shape rather than a circular shape. But this is also a culvert, and we can analyze its hydraulic capacity in HY8 regardless of whether it's circular or rectangular boxes. Sometimes it's common to allow a natural channel underneath the culvert, so that the culvert is only providing a structure for the road to go over, and if you can, trying to preserve the natural flow of the stream underneath. In other cases, you can see that there's been some scour under the culvert, some hydraulic scour, and when the flow rate gets really high, there's a lot of energy that's being exerted on the bottom of the channel. And the scour can, if there's fissures in the rocks, or if you have like a blocky or like aggregate on the bottom, it can wash all of that out during high flow conditions and undermine the strength of the foundation potentially. Sometimes culverts are just as simple as a projecting pipe, and so it can be made out of a variety of materials, and it's meant to convey water under a road. And they're used because they're so much less expensive than a big fancy bridge would be. And they're generally used for much lower flow rates. We wouldn't be able to put the entirety of the Thames River through this culvert like you can under London Bridge. But for a lot of the small watersheds that are going to be along a two-lane divided highway in West Virginia, a culvert's going to have plenty of capacity. The way we figure out how big they need to be is we first look at the hydrology and find what flow rate we're going to have to be carrying through the culvert. And this says the flow rate that will occur over certain recurrence intervals. And we don't have time to get into a lot of details with the idea of recurrence intervals, but that is just a storm that comes around every 2 years is going to be smaller in size than a storm that only comes around every 10 years. And so what we have to figure out is, this pipe that we're putting underneath the road, should it carry enough water to handle a 2-year storm, or a 5-year storm, or a 10-year storm? Like, how often do we want the water that's going to be passing through that culvert to be more than the culvert's capacity? And an interstate highway, like Interstate 64, for instance, is supposed to be designed so that it only fails during a 100-year storm. It's supposed to be able to carry all of the smaller storms. So a 50-year storm, one that's so big it only comes around once every 50 years, that's not going to have water accumulate on the road of an interstate highway if it's been designed correctly. But a small 2-lane county road, you're not going to have the funds available to design every hydraulic structure in the county to that same 100-year standard. So you pick the roads that have the most traffic, the highest speeds, serving the most people for the high standards, and then you would apply lower standards to other less important roadways. In the end, it's a safety issue, but it's also an inconvenience issue. And so there are certain roads where people are going to be driving more slowly, and there are fewer people that go over that road, so it doesn't really matter quite as much if it's occasionally submerged. So it's partly about the flow rate, and it's partly about the shape, the size, the slope of the pipe. And so it's a combination of those two things that tells you how big of a pipe is needed. Now, this is showing a lot of different inlets, and when we go through HY8 to do some calculations, we're going to have to specify whether there are head walls and wing walls. So the head wall is this, that's right in the immediate adjacent area to the pipe. The wing walls are guiding the flow into the pipe. The pipe could be projecting or it could be mitered, which means that they've kind of matched the edge of the pipe with the slope of the roadway. And sometimes there are just precast end sections that can be put into place really easily that try and guide the flow into the pipe, but they don't have to be put into place in situ, which is more expensive and a little bit trickier. If it's built in a factory, it can be done right to specifications and then just put into place in the field. And it's high stakes sizing a culvert, because if you don't have enough capacity in the culvert, then the end result is that flooding can occur. Now this is a picture, a series of photos that was taken. The water flows from up here through a culvert and into a creek downstream of the culvert. And so there's a culvert that goes under this road, and you can already tell that something's gone wrong. And what went wrong was the culvert was too small, and the water level got high upstream. You can kind of just see it here. This is water in the edges of the tree. The water level got so high that it was pushing flow around the side of the culvert. Not only through it, but water was seeping through the soil that the culvert was embedded in, and it was washing out some of the soil particles, and so there was what's called piping, where actually the soil that's around the culvert got washed downstream, and then it collapses, and now the water can seep at a higher velocity, and it has even greater scour potential, and so it eroded and undermined the entire foundation of the road underneath the culvert. So it just gradually was failing and washing away worse and worse until eventually you can see here in this photo that quite a lot of damage has been done, and this road's going to be closed for a long time because the headwater depth was getting too high and there was so much pressure that the seepage caused a failure of that foundation.
Well, there's plenty of room for a proper culvert now, right?
They may even put in a bridge, right? Yeah, maybe they should have done a bridge in the first place.
Now, it wasn't like a once in a 100-year storm. They couldn't always predict it that the rainfall would be that bad.
Well, this semester we're going to look at some data sources that we have available that it shouldn't have been that much of a surprise. I think that probably whoever designed that isn't working as an engineer anymore.
Probably.
Yeah. I mean, we all make mistakes, but
results in that big of a mistake.
yeah. I think that this one was probably, I mean, unless it was installed wrong, and that's possible. You know, like if the soil wasn't correctly compacted around the edges of the culvert, then the piping could have occurred more easily than it should have. But without knowing all the facts, just my suspicion is probably the culvert wasn't as large as it needed to be because too much water was accumulating upstream. All right, so how much water can make it through the culvert is partly depended by the inlet conditions. And the inlet conditions are meaning like what is the channel upstream and what's the depth of the headwater compared to the diameter of the pipe. And so in inlet control, that's usually occurring when you have supercritical conditions. Now, some of you haven't had hydraulic engineering yet, and so you don't know the difference between supercritical and subcritical flow, but for today's purposes, just assume that the water is moving quickly through the culvert when you have inlet control. So it's characterized with high velocity of water, both in the natural channel and in the culvert. And the most common thing for us to do is to put the culvert down so that the bottom of the culvert matches up with the original channel. The bottom of the culvert is called the invert, and so the most common thing is just to put the culvert invert matching up with the bottom of the original channel that was there to begin with. So that's inlet control. In outlet control, you have relatively shallow slopes. And so the pipe isn't at the same slope because the stream was kind of a slow-moving stream. And so subcritical conditions meaning that the water velocity is low. So that's usually what happens when you've got outlet control. Now, if you're going to be sizing culverts manually, there are these things, these tables and books full of nomographs. And a nomograph is a graphical way of performing calculations where if you know 2 points on a curve, you can predict the third. And so, for instance, if you knew the size of the pipe and the flow rate that was going to be going through the culvert, then this would tell you the required slope, for instance. And so nomographs can be used to perform calculations that the computer, in our case, is going to be automating for us. So we won't have to apply a nomograph, and for that matter, you don't have to determine manually whether it's inlet control or outlet control. The computer will tell you that, but I wanted to tell you like what it essentially means is that inlet control is when you have high velocity conditions and outlet control is low velocity conditions. Here's just to compare and contrast what a culvert looks like when you've got lots of money versus what a culvert looks like when you don't quite have as much money in your roadway budget. This is a photo that I took in the United Arab Emirates, just outside of Dubai. It's a series of arch culverts where the water's coming out of the mountains and they don't want it to wash away a really important road that's connecting Dubai to the, I guess that's the eastern coast of the UAE. It's pretty big. To give you an idea of the size, I'll show you, here's the height of a person compared to the size of the culvert. And so I think the top of the arch is probably, 12 feet high. And they recognize that there may be a possibility of what's called overtopping. And you'll notice that here's a bunch of gravel and rocks, but then there's also a mesh on top of that. And why do you suppose they would put a wire mesh on top of those rocks?
So they don't get washed out.
Yeah, it's because they don't want those rocks to go anywhere. Now, why take the mesh all the way to the top? Isn't the water just supposed to be going through the culvert? But they've got this cage to the very top. And the reason why is they know that sometimes the water is going to be going through the culvert and it's going to be totally full, and then there's going to be even more water. So the water can either go through the culvert, or if it keeps getting higher and higher, it can go over top of the road. And so that's a condition that we're going to look at with the program as well, is how much of the flow goes through the barrels versus how much is going over the roadway.
Did you know this was here, or did you just get excited when you saw it?
I got excited, got pulled over, climbed down there with my camera and took pictures. Yeah. It's on the way to a cool part of the country called Hatta. All right, this is what a culvert looks like when you don't have as much money. They don't want scour here, and so they're using some roadway signs to keep it all together. What I think is ironic is look at what this sign says, highway safety. So that's funny, right? So it's doing the job. All right. So the easy way to size culverts so that you don't have to use nomographs and diagnose what is the flow condition is HY8. And I've mentioned that you should download HY8. I'm going to do a quick demonstration of it today. Apparently these computers have version 7.5, and version 7.5 is mostly similar to version 7.6, which is what you'll download and install if you get it directly from Federal Highways. It's great, and it has a graphical interface that when I started teaching back in 2005, this program didn't have a graphical interface. It was kind of like using a DOS program, like from the 80s or something. And the program's a lot easier to utilize now that it has its graphical interface. What we're going to do in the 6 minutes that are left is kind of try and visualize this culvert and then put it into the program to see if we can figure out what's happening with the water that's going through here. So this is a top view. You can see it's a 2-lane road, and here is a stream. The blue stuff is water. The flow direction is from the left towards the right. We can see that this is a rectangular channel, it says. So by rectangular channel, that means that the side walls are vertical, and the bottom width is that parameter of 5 meters. So the culvert, here's the road, and then there's some sort of a pipe there. If we're looking at it straight on, and the width is 5 meters. The slope that's measured, S0, that's the channel bed slope, and so this is a relatively shallow slope. It's less than 1% slope. In HY8, sometimes lengths are defined by station. And if you've worked for the highway department or maybe an internship where you had roadway plans, you maybe are already familiar with the idea of stationing, but they're just kind of distant measurements starting with a certain point as a datum. So like if this part of the road was defined in the plans as 5 plus 00 and this is 5 plus 35, then the place where the channel ends and the road continues would be 5 plus 40. And so we'll also sometimes define the downstream direction by stationing, and so the length of a culvert, where the pipe is going to be going underneath the road, the length of the culvert may also be defined by stations. This is the side view. So what I drew on the whiteboard was a front view. This is a cross-sectional side view of the culvert. And so you can see the inlet of the culvert pipe is at 1 + 0, 0, and the outlet station is 1.20. And so that's how we define the length of the culvert is 20 meters. Okay, this question is asking, would we be okay if we put in a 24-inch diameter culvert? And by the way, 24 inches is 610 millimeters. The rest of this problem is in SI units, and so I'm going to analyze this culvert to find out if we'd be okay, meaning, is there going to be no overtopping if we're trying to carry 25 cubic meters per second. Now this N value is the roughness of the channel, it's the roughness of the stream. So we've only got 3 minutes left. Oh, I wish we had just a little more time. All right, let me open up the program and show you how we would start to put this data in. So we're going to create a new project and add a crossing. And then we have this screen where we're going to start telling it about the minimum. Oh, okay, first things first, it's in CFS. So I need to close that and change the units from US customary to metric.
So do we use map features to locate or add a culvert crossing?
Add a crossing.
Okay.
All right, once you put it into metric units, my suggestion is to close the program and restart it again, and then double check to see if it retained the SI units. Oh no, it's back into customary again. I want SI units, and now I'm going to add a crossing. Okay, so now everything's in cubic meters per second. So our minimum flow, I want to just look at what happens between 0 and our design flow of 25 and a maximum flow rate of 30 cubic meters per second. Tailwater is the channel downstream. And the channel downstream is rectangular with a bottom width of 5 meters. And the channel slope that was defined here is 0.0025. So 0.0025. The Manning's N is the roughness of the channel, so like the rocks or the dirt or whatever it is at the bottom of the channel. 0.05 is the Manning's N value. And then the channel invert in the tailwater, that's asking what's the elevation of the river when it matches up with the outlet of the culvert. So 299.95 is both the elevation of the bottom of the invert of the culvert and the channel elevation. So 299.95 is the elevation. And if you click on view, what it generates is a rating curve that tells you when you have a certain flow rate going through that channel, what's the depth of flow. So it's solving Manning's equation to find out for a certain flow rate and for the geometry that you've described in that channel, what would be the Y, the normal depth, assuming uniform, steady flow. So you don't have to view that, but it's available if you want to get an idea of what's the capacity of the channel downstream. All right, 9:50. We're out of time. So what I'm going to do is I'm going to take a screenshot right here to remind myself how far we got. And I'm going to paste it into here so that when we start up on Friday, we can begin with the same data. In the homework that you have, you can work on the Parshall Flume problem, although we haven't yet gotten far enough for you to make any meaningful progress with HY8, you can start working on the Parshall Flume. So let's just end by taking one last look at the announcement slide. The homework's not due till Wednesday, so we'll have plenty of time after we go through the HY8 examples in class on Friday for you to do that.
So how do you make the SI